All right.
Yeah, and
Let's start.
No.
You might notice that some theorems have been added to the wall. Those are our 4 theorems we're going to talk about for this section. One of them we've already discussed a little bit. We'll add for a theorem list. And the other 3 are kind of applications that are really common when it comes to this integral. So let's talk about our theorems. Let's get going. Theorem 4.9. This theorem has a very special name in calculus. It is called the first fundamental theorem of calculus. It states that, and we've actually seen this theorem from last time. It states that the integral and the area are connected by the formula. The integral from a to b of f of x dx is equal to capital F of x evaluated from a to b, which is equal to capital F of b minus capital F of a, where f is the greater function, the result of the integration. So, this gives us a connection that exists between our 2 fundamental parts of slope functions versus area functions. The integration of this formula, the first fundamental theorem of calculus. As you can imagine, there's more than one fundamental theorem of calculus. This is just the first one. For today, it's going to be a lot of theorems, and then some examples we'll fill out most of the rest of the week. Theorem 410. This one is called the mean value theorem. Or the MVT. Now, I'll write the theorem first, and then kind of explain where it comes from afterwards. A to b of f of x dx. You notice that this b stays consistent. What is it equal to? F of c of b minus a. Now, what does this tell us about the mean value theorem? Let's remind ourselves. This supposes or proves the existence of some value c such that this is true. Let's remind ourselves what each of these components means. This first piece, as we've already defined it from the last section, represents the area. So the area is supposed to be equal to f of c is some y value. In other words, some height. B minus a is some width. Remember, b and a are both x values. And so b minus a would indicate the width of that bottom piece. Of course it is. So, what it assumes is that for every single integral, there exists a y value that is the average height, or the mean value, the middling value of this function. Now, the mean value theorem by itself has some minor uses. There will exist at least one place on this function that represents the height. However, the common application, otherwise known as the corollary, to this theorem is simply reorganizing this information. There exists an average value which is equal to 1 over b minus a times the integral from a to b of f of x dx. These two are directly related to each other. You can find the second one by dividing the first one. They used with slightly different reasons for slightly different purposes. For example, this one, there's multiple places where this value could already exist. This one just tells you what the value is. And so you might find that for a function, there might be 3 or 4 or 5 places that are the exact middle value of that function. It could exist in multiple locations. Because again, in this case, f of c has to be related to the function, right? It's some number plugged into f. So it has to be on my graph. To put simply, if I was to draw a rough picture of this situation, start by defining an area. Let's just go with a simple pump design. And say, hey, how do these two theorems meet? Well, the first theorem says there will be places, f of c and f of c, which would create a rough average area. Whereas the second version just tells you the value itself. It doesn't tell you where it's at, doesn't tell you how you get there. It just finds the value itself. This plays into a unique idea in calculus, which is that we can what's called squaring or rectangulating the area. Meaning any weird shaped area, we can assume is just a rectangle of a very specific size and width. Which makes a lot of sense. No matter how complex you make a shape, I could rearrange all of its pieces and all of its values until eventually I get down to some rectangle. So, our first two theorems. Theorem 411. The second fundamental theorem of calculus. Supposes the following. The derivative with respect to x of an integral evaluated from some value to x of a different function is as follows. In other words, the derivative and the integral naturally cancel on the finite range. This also gives us the ability to rewrite functions in new forms using calculus. So whereas in algebra you can do a simple substitution, here we can do a simple integration derivative cancellation in order to get a function to change values. So from t to x, from x to y, from y to z, or some other variations. In this particular function, the derivative and the integral will cancel, allowing for the function to change variable. This is the first connection that goes between the two parts of calculus that matter so far. The derivative rules and the integration rules. They both fit into this problem. I can use the integration rules to solve a derivative problem. I can use derivative rules to solve an integration problem. They're designed to fit together. And our last theorem of the day, theorem 412. The net change theorem. So far, the first three theorems we're going to talk about, 9, 10, and 11, they all deal with just solving an equation. Not a lot of real-world application to that. Theorem 412 is a real-world application. What it's primarily used for. So, I'll start by writing it out, and then we need to discuss kind of how these pieces all fit together. A to b of f prime of x dx is equal to f of b minus f of a. Okay, let's talk about these pieces. In this case, f prime represents some physics function, whose derivative would therefore make it a velocity function, or a rate of change function. This is somehow a changing function over time. And what you can do is, the integration of that changing function transforms it into its basic function. So this allows us to take the integral of a velocity function, will determine the net change, which we might call, depending on the application, distance, displacement, we can go farther in the physics with these than we need to. There's a similar process that we go from the acceleration function to the change of velocity function. These are our 4 theorems, and this is all the notes for this week. That's it. Relatively simplistic. The rest of the time this week will be spent primarily focusing on how to apply these theorems, practicing the integration rules, and knowing how these theorems fit in with the application of the problems themselves. Now, the first theorem is like last week. Can you integrate it correctly? It doesn't really tell you much more than that. The second theorem applies specifically when we want to know if there is a mean value, an average value. If we want to know where that is in the function. The corollary is applied primarily when we want to find that value itself. It's the difference between the average exists when x equals 3 versus the average is 7. They're 2 different ideas that are related to each other. Again, one tells you the location of the average, one tells you the actual average itself. And then finally, our second fundamental theorem connects together derivatives and integrals directly. And our net change theorem applies this to actual real-world problems involving physics. Yay! It's Monday. We're done with notes for the week. The rest of our time gets to be spent integrating. Yay. Everybody's favorite part of calculus, integration. Alright. Before we look at the integration process, thesis. Yeah. You make the pen, but not the pen. Questions about our theorems. These are unique theorems. I haven't done a great job of explaining them because they require context, which is what we'll be getting into. But so far, first impressions. What do you think of our 4 theorems in the corollary? Nice. Nice.
That's it. Nice.
They all look kind of similar. There's just some chicken walked across my page making random marks.
The chicken made these random marks. Oh god.
It's a very intelligent chicken.
Yeah. Oh man.
So, it is important to note that these theorems, they are very similar to each other. It's their main application where they have a big difference between them. So while all 3 of these, or all 4 of these involve integration, what they're used for is slightly different for each one. Let's start with the simple stuff. Can you integrate? Let's each remember from last week. Those cheat sheets will be helpful here if you have them. So let's pull them out. I'll post 3 problems on the board and ask you to integrate them. No, thank you. I'll give plenty of homework problems, I promise.
Double whatever you were going to give us originally.
Okay.
No, triple.
So that'd be difficult to do triple.
Give us a test in the last 5.
Double would be easy. I was going to do every other odd, but I'll just do every odd.
Yes.
Alright. Integral from 1 to 2 of x squared minus 3 dx. 2. Integral from 1 to 4 of 3 square root of x dx. For 3. Integral from 0 to the power 4. Let's take a square root. Yes. Alright. Give a minute or 2. This is a lot like last week. So as a reminder, what do these pieces mean? This first problem tells me the area between x equals 1, x equals 2, the x-axis, and this function. It's the area bounded by this particular region. And so this creates a unique looking shape, which we have to find the area. Number 2, same thing. In this case, the area we're defining is when x equals 1, x equals 4, the x-axis, and 3 squared of x. Last one represents the area defined between when x equals 0, x equals pi over 2, the x-axis, and secant squared x. So we'll take a start on those. And pull up a picture of all these so you can get a good idea.
There's a pi over 2 and pi over 4.
Oh, should be pi over 4.
Right.
Thank you for correcting me.
Dude, he's on liquid nitrogen. What a legend.
Yeah. This guy's idea seems terrible. A liquid nitrogen fueled computer. It would just create a lot of moisture. Just bad.
Not bad enough. Make it worse.
It's bad. Alright. In this case, we're registering this area that exists. Oops. Between 1 and 2. So this first function between 1 and 2, this area right here. Ricky.
Yeah.
Doing visual analysis, so not trying to find the exact solution, but just recognizing the picture. Make an assumption about what the final solution is going to be.
Negative.
It's going to be negative. Why is that?
Because a majority of the area is under the x-axis.
Beautiful. Fantastic. Okay? The majority of the area is under the x-axis, so we would assume this answer is going to be negative. It's a good spot check you can do to make sure your answer is correct.
Dang.
It does require the ability to graph the function though, so let's now take the time. Let's find a solution. We'd start by integrating the function x squared minus 3. I'm going to use the standard power rule, which states that you add 1 to the power, then divide by the new power. So x squared becomes x cubed divided by 3. The negative 3 becomes negative 3x divided by 2. We then plug in the 2 first, so 2 cubed over 3 minus 3 times 2 minus the 1. 1 cubed over 3 minus 3 times 1. And we end up with the final solution of negative 2/3. So, Ricky, you were correct. There is more of this underneath the axis, so therefore we do get a negative solution. Remember, it's bounded by these 4 pieces. On the left-hand side, x equals 1. On the right-hand side, x equals 2. X-axis provides a boundary, and x squared minus 3 provides a boundary. All right. Second one, integral from 1 to 4 of 3 square root of x. Now, as we talked about when we did derivatives, it may be responsible for you to actually take the time to convert the functions into power form. Power form is better. In this case, this would become the integral from 1 to 4 of 3 x to the 1/2 power dx. And then integrate using the power rule. When I integrate, I'd add 1 to the power and then divide by the new power. So the 3 stays at 3. X to the 1/2 becomes x to the 3/2. Add 1 to the power. Divided by the new power. 3/2. Evaluate it from 1 to 4. me go ahead and pull mine up now. Yes, power 4. So we have 3 square root of x evaluated from 1 to 4. So from 1, which is there, to 4, which is there. Sydney, tell me something about the solution. You positive? Okay, I'm going to force you to go farther now. Will the solution be, do you guess, bigger than 3 or less than 3? This is a fun check you can make on your own. Take a look. Everybody else, I'm just putting her on the spot, putting all of you on the spot. Look at this picture. We're defining the red area. Will this red area be bigger than 3, less than 3? Why bigger? Because it's just bigger. One thing you can do is remind yourself that area can be defined any way we want it to. So I might define it as a rectangle. In this case, a rectangle, this side would be base 3. Remember, it starts at 1 and at 4. This height right here, I could plug in 1 into this function to determine its height, or I could estimate it from the graph. We have a height of 3. This side would have a height of 6. And so just this portion of it is a 3 by 3 squared. Just that portion is 9. So you better believe it's bigger than 3. It's much bigger than 3. Okay? There were a few problems in your homework assignment last time, and let's do tonight. Specifically say, is your estimation going to be bigger than 3, less than 3, or some variation on that? Okay?
The last part, that's what it's saying.
No, 4.2 is tonight.
Oh, I just heard it 4.2 yesterday.
That's all. So, in this case, visual skills can be very helpful here, and keeping basic skills intact can be really beneficial too. Example, I know for a fact that that bottom piece, which is part of the larger picture, has an area of 9. Since that 9 is part of the bigger piece, the bigger one has to be bigger than that number. So the question your homework didn't actually ask to find a solution. Someone just said, hey, estimate the area based upon the picture. Is it closer to this number or a different number? Is it closer to 12 or 20? Estimation is really helpful here. All right, go ahead and finish this. I plug in my formula. Plugging in the 4, plugging in the 1. So I get 3 times 4, so 3 halves power, over 3 halves, minus 3 times 1, so 3 halves power, over 3 halves. You notice I haven't simplified this. If I'm doing it by hand, I probably should. Like, it would be very helpful. So I plug them in. Let's see. 3 halves, I would end up with 16 minus 2, so 14.
Yes.
Yeah, the area is in fact bigger than 3. Look at that. Last one. Yeah, secant squared. Nope, that's go secant. I want secant squared. Cool. Evaluated from 0 to power 4. So from 0 to power 4. Is that power 4?
I think that's 1.
I think that's 1. I think you're right. Power 4 would just be a little less than 1, right? But there. That area. Found it between 0, pi over 4, the x-axis, and the function. Abby, give me your best guess. Have you solved the problem yet?
Yeah.
Never mind then. Lame. Working fast. Let's see how it is. It is often a great idea to get a picture and give it estimate. Just to see if you're right.
Escape to the object, please.
What did you give the value? That's right. Then do my simple calculations here. Integral of secant squared is tangent. Evaluated from 0 to pi over 4. And then plug in the tangent. Tangent of pi over 4 minus tangent of 0. Tangent of 0 is 0. Tangent of pi over 4 is 1. 1 minus 0 is 1. Yay! Integration! Yay! 5 more problems are just simply can you integrate. There'll be a lot of rewriting the function in order to get it into a rule that does work, but they're pretty basic. Some good trig functions will be in there too. Some will also ask you to define the area. So like what I've done up here in purple. This area is equal to x equals 2, x equals 1, the x-axis, and x squared minus 3. Is that bounded region? Other questions will ask you to sketch. If you have a guide calculator, that can be of assistance. Okay. This is, again, the application of our first theorem, our first fundamental theorem of calculus. Pretty straightforward. Just be able to find a solution. Notice there's no real applications to this because you're not actually doing much with the actual math itself. You're just using actual skills to find the solution. We're finding areas. Yeah. Let's talk about some special cases. Some weird things that can happen. There are some functions, some very specific functions, that do not look like they're solvable with the basic integration rules, but actually are if you are creative. So I pose to you the following problem, which I give you the next 5 minutes to solve. Ready? This one will not be under basic integration rule. Even if you know what use substitution is, it will not help you.
Yay, useless. Just like this.
Solve. Get 5 minutes.
Give us 3. You finished? Jesus, the area always exhausted.
So what does this tell us, Ricky? That the area has to be positive, right? Because it's over this absolute value symbol, right? But I don't have any way to find that symbol directly.
Yes, you do.
Sure I do.
You can just do like animated integral and just that work. No, maybe that's not right.
You're on the right track. It is a requirement for problems like these that you have to rewrite them. You have to find some way to change this function. Absolute value is not on our list. So you have to find a way to rewrite it. So how can we rewrite the absolute value of 2x minus 1 dx? Oh wait, sorry. It's not from 1 to 3. It's from 0 to 3. As a reminder, that's what our function looks like. Absolute value, 2x minus 1. And we're finding the area between 0 and 3.
Solve geometrically.
That'd be an option, right? Solve it geometrically. If I was going to do that, how would I do this problem?
Accurate here. Wait. One half base height. There we go.
So we could. So I'm going to write the actual steps up here. We'd have to break this into 2 areas. The first piece is a triangle that's from 0 to 1/2. The second one, the triangle switch 1/2 it into 3. We could then solve it geometrically as 1/2 base times height plus 1/2 base times height. That's actually a fantastic approach. As long as we can find both bases and both heights, we can do it this way. In a second, though, I'm going to show you one where this is not one you can break up geometrically. Which is why for this problem where it's simple, I'm going to show an alternative. So this method is fantastic for this particular example, and a common one to try if you see an absolute value symbol. But if you can't, let's say I make one small change. What if it was 2x squared? Now it's no longer geometric. So how could I approach the problem now? Well, it turns out there's a system you can build that will always find the solution if you take note of how it fits together. Going back to our original. Here. Let me show you the system. It states the following. Every absolute value is equivalent to some piecewise function. What? Piecewise? They make a comeback? Yep. Yeah. Now, there are two versions of the piecewise function. One version, which is the same as what's inside. This is when the result is positive. There's a secondary version, which is a negative version, which occurs specifically when the result is negative. Think about it. What's the absolute value do? If it's negative, change it to positive. Positive doesn't do anything. This function, 2x minus 1, let's now take the time to compare it to the absolute value. It's the original function comparing it to the absolute value version of it. 2x minus 1. What's the difference? At one spot, right here, there's a sudden shift that occurs. Now to the right of that point, everything's the exact same. I mean, if I go up here, this integral, which we know is positive, is no different than that integral. The difference being that integral is solved. Because the result was going to be positive anyways, that right-hand piece doesn't need the absolute value symbols anymore. What about the left-hand piece? Left of that point, the function normally ends up below the axis. We want to somehow make it turn up above the axis. So what change are we going to have to make to that left-hand piece? Yeah. Because this piece was going to be negative, we have to change that absolute value to a negative version of it. Because if it's going to be positive, you don't have to make any changes. This is a common trick for absolute value functions, is to find the split boundary, a place where the function stops acting normal, and use that split to split apart our integration, which we can do according to Theorem 4.7. And with that theorem, we now make this a solvable function. Now, Michael was great to point out that we could just bring this solve problem geometrically. Some of your homework problems you could do geometrically. I'd strongly encourage it. But if they're not problems that do break apart geometrically, this approach works equally well. But to do it, note the steps. So when you see an absolute value problem, some steps you can take. What you're going to do is you're going to be split the integral Now it turns out how you split the integral is actually pretty easy. You split it where what's inside the integral is equal to 0. So notice I split it at half. That's when 2x minus 1 is equal to 0. So split it along the a equals 0 value. Whatever that value is. If there's more than one value, you have to split it more than one time. Once you split the integral, determine positive and negative using location. Was the original function going to be below the axis? Negate it. Was it going to be above? Keep it the same. This is a common household trick when it comes to these absolute value functions. That's why there are no absolute value rules. It's because we don't ever integrate an absolute value function. You rewrite it every time. If you ask me what's one rule that I would want to add to my cheat sheet, like an example of this would be fantastic. This makes a pretty good simple first example, which I'll redo over here, going through all the steps one more time. I would make sure somewhere in your notes you have a good, clean example or two of this problem, and we'll do another one next time as well. Showcasing how to take this particular function, split it along its boundary into its two component pieces, decide the sign, and then find our solution. Here we go. Let's redo this problem from the beginning. Integral from 0 to 3, absolute value of 2x minus 1 dx. Step 1. I'm going to start by taking 2x minus 1, letting it equal 0. This is my step 1. This is going to determine my boundary point. When I do that, I add 1 to both sides. I get 2x equals 1. If that was by 2, I get x equals 1/2. This is my split, and it's the first thing I decide. I then rewrite the integral as between 0 and the 1/2 of 2x minus 1, and between 1/2 and 3. Now this might feel a lot like what we did in the derivative problems. I can test around this split point to see which one it's going to do. If I test, for example, to the left of the 1/2, and it ends up being positive, well, I'm going to keep it the same. If it ends up being negative, I'm going to need to switch it around. So, now I decide, step 2, the signs. What I do is I take that 2x minus 1, and I plug in numbers to the left and to the right, and see what happens. So if I plug in 0, 2x minus 1, if I plug in 0, I end up with a negative number. What does that tell me about my integral? It means they take my integral and make it negative. If I plug in 1, the result is positive. Which tells me that when I pick this function, I make no change. Now this is now solvable. The previous one was not. We'll start tomorrow with another example of these integrals of absolute values, and then we'll look at some more of the other theorems, the mean value theorem, the second fundamental theorem of calculus, the corollary to mean value theorem, and the net change theorem. There's very little notes for the remainder of the week. A lot of examples, though. I strongly encourage putting some examples in notes, because some of these are still different. Questions from today? All right, let's go. A few minutes to spare. Look at that.